So now I would like to welcome and invite on the stage Yves Jacquier with his crowd. Yves is head of Ubisoft Laforge, and Yves will spoke about what is Ubisoft Laforge, and they will present some AI and machine learning project they are doing at Ubisoft Laforge. So please welcome Yves Jacquier. Thanks.
Hello. So first, thank you, Sacha, for the awesome organization. And first, also thank you, Mike, because you made my life way easier by presenting so many things we have in common here. So I'm going to very briefly explain you what Laforge is all about, and then let the real greedy stuff be explained by my colleagues here. As you know, artificial intelligence and video game, it's an old love story. If we go back to the basics, games are all about skills development. I have a kid, and I can witness that she's learning a lot through games. First, aligning shapes and colors, learning how to socialize also. Whereas, if I summarize what AI is all about, it's human-grade decision-making. So, in the history of AI, very often games, and then by extension video games, have served as ways to test the quality of AI. How good is my AI compared to a real human? And we all remember Kasparov versus Deep Blue 21 years ago. So while games and video games are serving as benchmarks, there's also another relationship between AI and games. That's a modern game. How many of you are familiar with AAA games, like the big, huge games like Ubisoft is making? Okay, so it's worth the video. That's a modern AAA game. So as you can see, you can do many things. That's real time, that's happening in the game. You can do many different actions. You can drive drones. There's a simulation of San Francisco. There are people who have a purpose in the city. You can drive by day, by night, in the city, in the countryside. You can go on the sea, drive drones, race, and etc. So what does it take to do that? It takes a lot of different assets, a lot of different artists, and obviously many AI to connect all those systems. It means that throughout the history of video games, we have used AI as different tools to help create more rich and richer experiences. If the relationship between AI and video game is not new, still there's a new paradigm that is shifting. And well, unless you didn't hear about neither AI nor video game development for the last 3 years, you might be aware that there are many things cooking. First change comes in the way we are making games. AI is bringing new stuff, and Mike's shown many examples. The idea is that AI for us is a brand new enabler to create many things, a creator's assistant. Just like Rembrandt used to have many people helping him, even for itself, self-portrait. Many self-portraits of Rembrandt actually have been painted by other people. And we think that it's going to be the same more and more for the next 3 years in the AI field and the video game field. It's going to be changing a lot. Think about NPC characters in video games. Today, it's mixing up many different ingredients, such as animation and models and behavior and etc. And we think that it's going to be more holistic with AI in around 3 years. Second thing, it's what video game industry brings new to the table, and that's the same kind of idea that Mike shown with the Lego thing, which is now the game engines and the data within are simulators of the real world. So in other words, one can use video games for things such as reinforcement learning to either test new models into a video game, new models of driving, as an example, but also maybe to audit things. If you want to understand how a car will behave in such and such context, such and such environment, maybe one can use a video game simulation. Second thing is all about the data, obviously. So in the gaming industry, we got tremendous amount of very specific data, such as mocap, and we have students from CRISPR working with us. Felix, I don't know where Felix is here, working with us, dealing with this mocap data to create new things, and is doing an amazing job. We also have 10 years of code of Assassin's Creed, which allowed us to reveal our commit assistant, which is kind of the minority report of developers, something that predicts that a developer is about to commit a bug. And we released the paper on our website, so it's now public information, public knowledge. How do you do that? Obviously, we all know that AI is still pretty much on the academic side, so that's a path of innovation, going from the theoretical world, theoretical R&D, to a product. And if that's a scale of love, whatever the love is, depending on your value, money, attention, recognition, whatever, academic world is pretty much here. A good researcher is known for the quality and the quantity of his or her publications. Ubisoft, we are here. We're known for our product. We're not a lab. We're making product. And when you want to have those two worlds work together, it's very difficult because we're using the same words. It doesn't mean the same thing. Think about like talking about short term. It doesn't mean the same at all. That's what I'm calling the gap of wasted ideas. And that's why 2 years ago, we decided to bridge this gap with Ubisoft Laforge. And the idea is to bring in people from the academic world, people from Ubisoft, working together and focusing on prototypes. And the idea is that each of those prototypes have to serve both sides, have to be in the interest of Ubisoft, making greater games, but also in the interest of the academic world, enabling more publications, enabling the creation of knowledge. That's really what we're doing. In a nutshell, what does it take? It takes first a critical mass. So that's why we have now 20 people from Ubisoft and 20 students coming from 6 different universities at Laforge. It takes some means, obviously. We want people to take time, try things, fail, learn from the failure. And it takes also a lot of diversity, because we think that the best thing is really to have people, mix people together to solve a real world problem. We're not trying to bring up the best new algorithm that will make the standout of the week. We're trying to solve all together problem. And with infinite possibilities. That's pretty it. And now I will let Olivier show very concrete examples of things that we're cooking at Laforge. Thank you.
Okay, thanks, Yves. So I'm Olivier. I'm a data scientist at Ubisoft Montreal. And with my colleague Adrien, we're going to talk about applying reinforcement learning to the development of video games. First, at high level, what we're trying to do, like the holy grail, if you wish, is to build AIs that could play the games like players would. Of course, this is super ambitious. We are not there yet. We have more focused initiatives we're going to talk about right now. And we've been working on this project at Laforge, bringing people, like Yves said, with different backgrounds. So we have myself and Adrien, we have more machine learning expertise. We also have expert game AI programmers. And we also have, so far it was 1 student working in an internship. We have 2 more coming this summer, and we're looking for more, so if you're interested, come talk to us. So why do we want to do that? At high level, the kinds of applications we have in mind, first, they are about automated assistance, like for testing, to help with design, balancing. And of course, if we can build AIs that can have good behavior, why not put them into games and either have better AIs or build these AIs more efficiently than by hand-tuning them. So this is our high-level objectives, like the phone applications I'm going to talk about is more about the first part, and Adrian's work is more on the second part. So what have we been doing in For Honor? So if you don't know the game, it's basically a team-based sword fighting games with a lot of different characters with unique play styles. And it's very important that all these characters are balanced between each other. You also need to build AIs for these characters to control them. They need to be balanced also between AIs. They also need to be able to provide different difficulty levels to the players. And this requires really a lot of testing. So this is a lot of work for our fight designers, AI designers, development testers. And the goal here, by training AIs that can learn how to play the game, is not to replace these people, but is to provide them with tools so that they can do their job more efficiently. The kinds of algorithms and techniques we've been investigating so far to achieve this goal belong to reinforcement learning. So I go very quick for those who may not be familiar with reinforcement learning. The idea here is you have an agent. So the agent here is going to be the orange character. He's learning in an environment. The environment is everything he does not control. So that includes his opponent, the blue character. And at every time step of the game, the environment is going to provide the agent with a state, which is the representation of the world as observed by the agent. We don't learn from pixels, so we directly provide the game state to the agent, like the life of both characters, their distance, their stamina, the animations currently playing, and so on. So everything that the agent needs to know in order to take his action. His action is going to be selected in the list of all available moves to the character. And then the action is resolved. On the next time step, you receive the updated state, along with what's called the reward. The reward is what tells you whether the action you took was good or was bad. So in For Honor, it's a fighting game, so you get a positive reward when you hit your opponent. You get a negative reward when you get hit. And the goal of the agent is to maximize the total reward accumulated over the match. And he does that by optimizing his mapping from state to action. So this mapping, we use the DeepQ network framework. So this is basically a neural network which takes as input the state, so all the state variables. And the output of the network is what's called in reinforcement learning the Q value, which gives you basically the estimate of the reward you're going to get given the input state if you take each possible action. So the size of the output layer is the number of actions. And once you have learned this network, the optimal way of behaving is by always acting by picking whichever action has the highest output on the output layer. So this is a framework which has been made very popular about five years ago by playing Atari games. There has been a lot of improvements on the algorithmic side on this basic algorithm. We're using some of them. I won't go into the details here. It's more about what we can do with this kind of algorithms. Very quickly, because it's not an Atari game, we need to build this framework it's more complex in the big games like For Honor. So we have this framework where we have a Python code running the neural network, which can interact with the game engine in C++ through sockets, going through a C# code anyway. The idea is your agent, by interacting with the game, can collect some data. From the data, you can optimize your neural network to learn these Q values. So based on all the states, observations, actions, rewards that's what you collected, you can learn the weights of the neural network. And then over time, you just feed back into the interaction script, and you can get better and better behavior over time. So data collection is super important here. So that's why for this project, again, we can't run a lot of instances of a game on a single computer. So we built this special map where we can have multiple duels running in parallel. So in each cell here of the map, you have one agent learning against his opponent. And we can also speed up the game simulation. Actually, when we run it, we don't have the graphics so that it runs faster. And this allows us to learn a lot faster than if we had a single duel running in real time. Now, what kind of results do we see? So if we just look at the curve first, like the training curves, it learns, that's cool. So we can plot, for instance, the reward over time. You see it's increasing. So after roughly 1 day of training, it's starting to reach its plateau. We can also look at the win rate. So does it actually win? And when it wins, if you look at the life remaining at the end of the match, it tells you how easily it was able to win or not. And you see everything going up, so that's cool. You're happy. However, if you run the same experiments multiple times, you run into this problem that people in research on reinforcement learning know about, which is there's a lot of variance in the results that you can get. So these are 10 runs of the exact same experiment with the same parameters, and you see the curves are not exactly the same. And if we look at the policies that are being learned, we see they are not exactly the same either. So let's look at what happens. So here we have in orange again, the orange is the guy that we learn, and he's playing against the highest difficulty bots in the game. And what you see is the orange bot is actually, he's stepping back. So what happens is when he's sufficiently far from his opponent, then the game bot is going to run towards him and then is going to get hit. So this is a strategy which is very safe, and actually it highlights an exploit in the AI of a game bot. But the overrun with the same parameters, this one didn't work as well in terms of performance. He's still able to beat him, but you see he never reaches the same point where he forces his opponent to run toward him. So it's not exactly the same strategy. So the key lesson here is for a practitioner who actually wants to do this, like to learn his AI behavior, this is a problem because it means if you get the behavior you want on one run, maybe the next day it won't work anymore. So this is the kind of challenges you have to work with if you want to apply this kind of techniques in a production context. There are some techniques to actually keep some control of the behavior of the bots. Typically, you do this through reward shaping. So reward shaping is about how you define the reward to control, to encourage the bot towards certain behavior. So it's possible to do something, but sometimes it doesn't do what you want. So this is an example. I won't go into the details, but basically the bot here is about to kill his opponent, but he doesn't want to kill him. The reason is because it was a reward where he was given some points for performing some actions that don't actually damage his opponent. So he learned to keep his opponent alive just so that he could accumulate more and more reward. And that's not what we intended him to do. So we wanted him to do some actions, but eventually kill his opponent, but he didn't want to. So the lesson here, again, is in this kind of applications, it's still hard. Yeah, he really doesn't want to kill him, so he says, okay, come. So still, we still have a bot who's able to beat his opponent, even though it's hard to tell exactly how. The other kinds of limitations that currently prevent us from putting this in front of a player. First, it's a deterministic algorithm right now that we're using, so it's very predictable for a human opponent. It's not actually always finding the optimal way to play because of different weaknesses in the training scheme and the setup that we have right now. Also, we are only focusing right now on the core fighting moves of the characters, so we didn't try to tackle the difficult problems of navigation and strategic behavior, for instance. Also, human players are used to taunt their opponents when they win. Okay, that was an animation, which the bot didn't learn to do. Still, we do have some existing ongoing applications right now, so we want to use that to bring some added value to production. So one of them is continue what we've been doing so far, which is find weaknesses in the current AI to help with automated testing. The other one is related to what we call guaranteed hits. The idea is, For Honor is a complex game where in some specific situations you have very specific actions to take which are known to be optimal, and players build these huge spreadsheets listing all possible situations and everything you should do. And this is super important for balancing. So the goal would be to kind of generate this data automatically. Of course, if we can solve some of the limitations I mentioned before, we have other interesting things we can think of. Like I said at the beginning, help with balancing, and maybe at some point put the AI into the game to have more varied behavior, offer more fine-grained difficulty, for instance, and hope maybe at some point even replace human players. So that's the part on watchdogs, and now Adrien is going to talk about, sorry, that was for now. Adrien is going to talk about for watchdogs.
So thank you, Olivier. I will talk about the driving initiative at Laforge. So if you don't know Watch Dogs 2, it's an open world game where there's a lot of life in it. And to have life in a city, you need to have cars. So the original car is driven by a PID controller, and those PID are driven by hand design curves like that. And each vehicle has its own physics, and each curve needs to be tweaked for each vehicle. So it's a lot of time, it's really costly. And we had an idea is the account can just try to learn those curves with reinforcement learning techniques. So it's exactly the same thing than in Forerunner, the same framework. You have the car and just taking action in an environment. So I won't take a lot of time for that. It's exactly the same. So the reward is really important. It's the only signal that is given to the car to learn. So what we want to do is to follow a road. And for that, we measure two things, which is velocity and the distance to the road. And what we want to do is to have a distance equal to 0 with the right speed. So we want the car to follow the road at the right speed. So we had nice results at low speed. So it managed to just give him a path to follow, and it just managed to do it. And he knows how to turn, he knows how to stop. If there is an obstacle on the road, he knows he needs to stop. And when there is no obstacle, he just start again. You see that? Just a second. Yeah. So if you have a pedestrian on the road, the car is just stop. And then we just get out of the road, we just start again. So the controller there is just taking a path and tries to follow it. So what we learned, we managed to have a better controller, which is visually more efficient. As you can see, the PID controller is making some correction, it's more discrete to correct its error, while the reinforcement learning controller makes some smooth correction. So you can see there that the turns are more smoother with the overall controller. So we had something working at low speed. Let's unlock the speed and just drive as fast as we can. So we managed to just accelerate enough to reach the maximum speed of the car. But yeah. So what happened? Mainly, it just didn't slow down enough to take the turn. And because it didn't hit the brake, it was not a good solution to do, hit the brake. You just never hit the brake when you're driving at high speed just to slow down and to take a turn. That's the only thing you need to hit the brake. So the agents never discovered it was a good action. So we need to help him to discover it's a good action. So we came up with a solution that I like to call the stochastic brake. It's a really simple idea. It's just you drive and sometimes just brake the brake, just like that. And we did this only during training. So we force the agents to discover the action to hit the brake. And did it manage to learn? Let's see that. Yeah. So that's pretty impressive to see that, because the action to brake is really different from the original action to just drive at high speed. So let's dive into the step by step. Just arrive with a lot of acceleration, no brake, at high speed in a turn. When you just get into a turn, just stop accelerating, braking like full, slow down enough, and then when you just take the current turn, just accelerate again. So those are the results we managed to have with the driving initiative. So when we try to focus next on the drones, as you see on the video earlier. So let's talk about, really briefly, on the conclusion. First, there is a lot of limitation with reinforcement learning. For example, you need a lot of data. As Olivier said, just need to run a lot of agents in parallel. So this is the limitation. You also have no guarantee that it will work, because there is a lot of variance. You can start again and it won't produce the same results. And there is also a lot of different things that you cannot do with, especially, for example, long-term planning, which reinforcement learning is not good at. And the reward shipping could be a bit tricky. As Olivier said, there is a lot of the agents will try to exploit the reward and manage to find behavior that we don't want to. So it's not like something you just take and you just magically manage to create the perfect AI. That's not how it works. So you need to have some ML expertise. You also need to have the game expertise. You need to know how to program your bot. You need to know which states it needs to have, which actions you can do, and also build a lot of tools. But in the end, we managed to have solutions implemented directly into the engines in communication with Python scripts. And so the pipelines are already operational, and we have results that is promising for the next things. And there is a lot of internal expertise built that we managed to exploit for more projects. So thank you very much. If you have some questions, don't hesitate.
And we will leave some postcards if you want to keep some keepers from you explaining all that. Obviously, many projects as well. We have many internship positions open and etc. The usual. Thanks.